Okay, today we're going to look at the voltaic cell. So I asked you to cut out pieces, and so I want you to set up your pieces so that they look exactly like my picture here. So I suggest you pause the video and set this up. Once you have it all set it up, then you can hit resume, and we are going to work through the pages of modeling the workings of a voltaic cell, which you can find in your Schoology Chapter 18 notes folder. All right, so to start with, we're just going to kind of look at our model, and we're going to answer the first set of questions. All right, so I'm going to move out of my model here because you should have yours all set up. And I'm going to fill in the worksheet with you. Okay, so let me minimize this. Let me open this. Okay, so you are to notice there are 4 zinc ions in the beaker. So those are the green colored shapes. And then you're to explain why there are the number of sulfate ions present in the beaker. So if you're just looking at the half reaction of the zinc sulfate, the orange pieces with the black lines are your sulfate ions. And so if you look, there are 1, 2, 3, 4 of those. And remember, there were 4 of my zinc ions. And zinc is +2. Okay. So in other words, the reason why we need the same number of sulfate ions as zinc ions is so that the solution that we have in our beaker is neutral. Okay. And I would think that we would know from first year chem that when we talk about neutrality, it's because we have an equal number of positive and negative ions. So the net charge is 0. Okay, so then we were to complete the table. So we already counted that there were 4 zinc ions in solution. So then you're going to go to the other half reaction, and the little blue colored shapes are copper ions. And if you were looking just at the solution, not the electrode piece, you would see that there are 4 copper ions. And then we're going to look at the total number of sulfates. So you had to count the sulfate that's in the zinc solution and the sulfate that's in the copper solution, and you see that there are 8. Okay, so we completed that part of the table. Then we're going to go back to our model, and we're going to follow directions. Okay, so my directions say we are to find a zinc atom at the zinc electrode, and we are to remove 2 valence electrons. All right, so the electrons are the little black circles. So I'm just going to use this one that's on the top. We're supposed to move our electrons to the wire. Okay. And so our electrons are going to move through the wire from our zinc solution to our copper solution. And we're also supposed to now move the zinc, so it's no longer a solid zinc, it's now a zinc ion, so we got to move it off the electrode. And so once these electrons get to the other side of the wire, they're going to find a copper that doesn't have any electrons. So these electrons are going to join this copper ion here. And then this copper ion now is no longer an ion, it's an atom. So we're going to put that on our electrode here. Okay. Then it says you got to now examine how the number of ions have changed. Okay. So we have to reestablish neutrality in our solutions. Okay. So there's a semi-permeable membrane that's here in the center here. What you're going to see in lab is that you're going to have a salt bridge, so it'll be a piece of string that connects these two cells. Okay, but you can also have a semi-permeable membrane. Okay, so now the copper solution has one less positively two charged ion in it. So we have to give up one of these sulfates, so it's going to travel over here. And remember that this zinc gained a +2 charge here, so now we have neutrality again. Okay, so let's go back and let's answer our questions. Okay, so it says explain how the direction of electron flow in a voltaic cell is consistent with what you would predict from the activity series. All right, so this is directly related to our discussion from parts 1 and 2. Right, so what you probably remember from first year chem is that anything higher in the activity series can displace anything that's lower. Right now, for now, we're going to use the activity series, but you're going to see later on that we are going to use a different table to predict what we're going to find in each half cell. All right, so if I look at the activity series, zinc is higher, so zinc is more active. And so what this means for us is that zinc is more likely to transfer electrons. All right, and then we already did this part of our model, so let's look at this question here. So it says, explain how the zinc half reaction remains electrically neutral even though zinc ions are being formed from the neutral zinc metal. So remember, this is where we moved that sulfate ion from the copper half reaction to the zinc half reaction. So this gained a sulfate ion. Okay. All right. And so that means copper did the opposite. Copper had to lose an SO4 -2 ion. And so that purpose of that semi-permeable membrane or salt bridge is to allow ions to move so half cells remain neutral. All right, and then we're to identify two pieces of evidence that a chemical reaction has occurred as time passes with the wire connected. Right now, there's actually several, so I'm going to list all the possible pieces of evidence. One is that remember that our zinc electrode went from having a zinc atom to having a zinc ion. So what we would physically see in lab is that the zinc electrode gets smaller. Okay, and we'll stay with that zinc half reaction for now. And so this means we now have more zinc ions in solution. All right, so let's look at our copper half reaction. So remember, our electrons travel through the wire. One of the ions gain those electrons, so we formed a copper atom. So in other words, what we would physically see in the lab is that the copper electrode gets larger. And so what we see in our model is that there are fewer copper ions in solution. All right, and then these are just kind of reinforcing what we already know. So we already talked about that the one that loses the mass is zinc. And we get more zinc ions. And so we want to pick the half reaction where we're forming zinc ions. So this is the one we would circle. Okay. All right, now what we notice in this equation is that there is a loss of electrons. And so when we lose electrons, this is oxidation. All right, so far just what we've seen in the model, and we're reviewing what we should already know from chapter 4. All right, so the one that's going to gain mass is our copper. And it wants to know, where do the copper atoms come from? Okay, so remember what we saw in the model, that copper ions gain 2 electrons. Okay, remember those electrons traveled through the wire and became copper atoms. Okay, so now we're going to look for the equation that shows us that we've made solid copper and we're gaining 2 electrons. So here's our correct equation. All right, so here we're gaining electrons. And whenever we gain electrons, this is reduction. So again, a review of what we know from chapter 4. Okay, so here's where we get to the new part. Okay. So it tells me that the anode is where oxidation occurs. And we decided in our previous question that the metal that underwent oxidation was zinc. And the cathode is where reduction takes place. And we decided in our model this is copper. Okay. All right, so this is our new content, one of our new pieces of information for chapter 18. All right, I'm going to stop here, and then the next segment is going to be where we're going to draw the voltaic cell.